Okay, while we're waiting, camera start. We're going to be talking about support vector machines. But the idea today is vectors about classifiers. Everybody's familiar with SVM, right? But the point of my lecture today is not just to explain SVM, which some of you might know about, some of you might not. But then I'm also going to let you example it has to do with data stable classification. So here's the basic problem again. We're speaking of classification, and I'm going to be talking about binary classification. You have a bunch of training data. The blue data has a positive class, and the red data has a negative class. Positive classes are labeled +1. Negative classes are labeled -1. And we have to find a rule that correctly assigns a new test instance to one of these classes. So, for example, if I've got that green dot out there, what is the class of that instance? Now, if I'm using nearest neighbors, how would I actually perform classification for, or I won't call it nearest neighbor, but if I was performing neighborhood-based classification, which we've seen in past classes, what would the classification group be? Anybody? Yes.
Vote.
Can you speak up, please?
A majority vote.
A majority vote. What else did we look at?
Sorry.
Can you please speak up?
We could add distances for the reds and the blues.
So we said we could add up the distances for the reds and we could add up the distances for the blues, or more generally, they actually say we spoke of something. Now, here, what are we actually trying to compute? If I assign a label of +1 to the positive class and a label of -1 to the negative class, then this is a regression problem, right? For my test instance, I'm missing my y. I have the y's for the remaining data. And all I'm trying to do is guess the y for my test instance. Given this, how would I perform nearest neighbor classification? Nearest neighbors, there's no minimization. What am I going to be doing? Guys, somebody help me. Yeah.
Just take the average and take the sign of the average.
So we're going to be saying average how?
The average.
The weighted average. And what is the weighted average? One over the distance. It's not something simple. We looked at another measure of similarity, which was that.
Yes.
Cosine. We looked at the inner product, correct? And so I could just say x transpose x I. This is going to be my prediction, right? And I was going to be at the sign of this. Everybody remember this? Take a look at my data. Is every training data point equally important? No. If something is in the midst of a giant cluster of training instances, I could rule that out. I can get rid of most of them and I can still get the same basic classification rule, right? So if I want to account for that, what can I do? I can add a weight to each of my training instances. And so my classification rule can simply be some alpha I by I x transpose x. Again, for this to work, remember, we're normalizing a zero mean interference. Otherwise, much of what we do will not really work very well. But once we agree with that, this will make sense. You agree? Right? And so I can just say sign, because I want to decide if this belongs to the positive class or if it belongs to the negative class. Right? And so that's my nearest neighbor classification. Alpha I, because not all training instances are equally important. But then here is the question. How do I decide what these alpha I's are? Which training instances are important? How can I do that? Number one. And so here, this is the basic rule, right? So how do I decide which training instance are important? Oh, sorry. Thank you. So how do I decide which training instances are important? What would a standard approach to doing this be? I can just define an optimization function, correct? And I can minimize my optimization function. What would my optimization function be? I'm going to try to classify every one of my training instances because that's all the data I have when I'm training, right? And so what I will do is say for one of my training instances, I'm going to have I j, let's just say I, we need to say right. It's G instance. So for my J training instance, this is what is being predicted. And now, if this sign, this were the correct sign, then how do I know this is the correct sign?
You multiply it with the true label and it should be positive.
Yes, thank you. Right. I'm going to say J, and this is going to be positive. And the larger this value is, the more positive this is, correct? So I could just be saying maximize this guy. That makes sense? Right? Does this make sense? But then this is not enough because not every training data instance is equally important, correct? So then how can I account for the importance of the training data instances? This is the classification accuracy for the jth instance. How do I account for the importance of the jth instance? The j, thank you, right? Is this equation making sense to everyone? Right? This is what I would be. This is my accuracy. I would be maximizing. Yes.
The summation of I is for training and for J is for testing.
The j is also part of my training data, right? I'm classifying each one of my training instances based on everything else. And I'm checking how accurate it is. That's about it, right? And so if this is all I'm doing, then I'm going to end up with, I'm spending 10 minutes of class giving you something that's wrong. It's gorgeous. But anyway, so do you agree that this is summation I, j, I, j, y, j, except transpose. This is what we ended up with, correct? And you agree that this makes sense. This is something that I could be optimizing for the others.
Yes,
But then, yeah,
assuming restrict that's like the sum above a big one or something.
I'm making no assumptions about the alphas right now.
But you can just set the difference.
It can be accurate, right? So, what else do I want to be doing? I want to be making the alphas sparse. I don't want to be retaining all of my training data. I want to retain the smallest number of training instances. How would I do that?
Minimizing the L1 norm.
Can you repeat that?
The L1 norm.
The L1 norm. What do I want to do with L1 norm? Minimize it, right? So I would say minus summation alpha I if all of my alphas are positive. This is what I'd be minimizing, correct? Or alternately, I'd be maximizing summation alpha minus summation phi j alpha I alpha j by find the alphas. Let's solve this problem, correct? Everybody with me? Right, this is going to be minimizing. So this is what the solution seems to be like. And does everybody agree this time? You are going to see what perspective this makes sense. So the error measure for any training instance is simply going to be this guy here. For any instance, right? And so I can just be minimizing this term. And if I minimize this, I should be able to automatically find out the set of alphas, which alphas will become stars. And you're going to end up picking the specific alphas that makes the most, make more sense, right? Does everyone agree that this logic that we've arrived at is clean? Thank you, right? This is exactly wrong. I don't know why. But so yes.
So the thing that you are trying to converge on, that you're doing your gradient descent for, is to find the value of alpha.
Correct.
You are trying to find the value of the weights.
I'm trying to find out which are the important instances and how important they are.
Is this like a find the first n many weights? Or
Yeah, I mean, we don't know what n is, right? How do you order it? So this, we actually have a formula for finding the best set of alphas.
well, so will you get like a matrix alpha or a value
It's a
alpha?
vector, an alpha with every sharing instance, right? Okay, so every instance is going to be contributing some capacity. So is everybody with me until the last statement? And does everybody sort of feel sad about the last statement? You should, because I tell you, it makes so much sense and I just told you it's perfectly wrong. So I'm going to spend the next 106 minutes showing you why it's wrong. Right? Let's go back to our classification problem. This is again, we're given a bunch of positive and negative training instances, and we have to train a classifier to separate them. And we're going to assume for the 90% of the rest of the class that our classifier is linear. What do I mean by linear classifier? What do I mean by linear classifier? Yes.
Data is separate from that.
I can draw a hyperplane with a space which is going to separate the positive and negative instances cleanly, correct? So, and we're going to assume that the classifier is linear and the hyperplane perfectly separates the positive and negative instances. I will fix this, but then before I continue that, I'm going to do a little bit of algebra. What is the formula for a hyperplane for algebra? Anybody? So here's how I would define it, correct? Think of a hyperplane of some space, and this is maybe 5 inches. And if I have a vector here, right? This is W, and if I have a vector X, then if I tell you W transpose X equals 0, what does it tell you about the two vectors? Here. What does it tell you about the two vectors?
Orthogonal.
They are orthogonal, correct? And so suppose I just said, you're right, right? So what is this equation? W transpose X equals 0. Is the set of all x's that are orthogonal to W, correct? So this is the equation for a hyperplane which is exactly at 90 degrees. That is the simple, most trivial equation for a hyperplane to the origin. Everyone with me? Okay, so now suppose I update that, and now I want an equation that's not the origin, but it's the same hyperplane, but at a distance d from the origin. How do I derive the equation for that? Yes.
Still, yes, some weight costs.
How do you get there?
You can think of it as something to x translated by some amounts around origin, added over costs.
So it comes out, right? So at any point of this plane can be written sum of the components. So if I choose a point here, I can say this guy is the sum of, so let me call this vector x. This is the sum of some vector x spline on this plane plus a vector of length d along this perpendicular to the plane. Everybody agree? So how would I write that in algebra? I can write that as x equals x prime plus what? What's it going to be? What is the additive term going to be? BW? Is it BW additive?
Over W normal.
It's going to be d times W over norm of W. Why the divided by norm of W? It's d steps, the distance d along the unit vector in the same direction of W. That makes sense to everybody? So basically, I can say this. So I can say W transpose X, 3 multiply both sides by W, right? That's going to be W transpose X prime plus T times W transpose W over W. Correct? Can I simplify this?
First thing is second thing cancels out.
So can you say that Alex?
W transpose X prime is 0 because of the initial.
W transpose X prime was from X prime up there, right? You can see X prime up there. It's on the plane where W, that's going through origin. So W transpose X prime is, what is it? 0, right? So this was a thing. What is this?
1.
The distance from B. So this is D times normal W. Because W transpose W is not W squared, right? So in other words, I've got W transpose X minus D normal W equals 0. This is the equation for plane that's perpendicular to W and at a distance T from origin. Everyone with me? Okay. So I can generally write this as, if I give you the equation of a plane that's first W transpose X minus D equals 0. What is the distance of this plane from the origin? What would that be? That's going to be the same saying. B equals 2 times from W, right? So distance equals B over, right? So if I give you this equation, then this system, this is a plane that's at 90 degrees to W and at a distance B over log W from the origin. Everyone with me? Get the link. So, questions, anybody? We're going to keep building on this, right? I'm just going to be using this stuff. So this has to be learned in your lectures. So let's assume that this is all understood. And now I give you this thing, which is talking about these points. The plane is W transpose minus B equals 0. And I give you another point here, which is not on the plane. What is the distance of that point from the plane? So how do you arrive at that solution? So she's asked about the answer. How do you do it? Yes.
The way we did like B is equal to D mod D to normal.
So correct. I can find some X prime on this plane. Correct. And then this is a distance T, right? So X equals X prime plus D W on W as before. Correct. And so I can say W transpose X minus B equals W transpose X prime minus B plus D on W. Because this is a W transpose W divided by normal, right? And this we have here. Right? So in other words, the distance equals W transpose X minus B by W. So basically, to find the distance of the point from the plane, all we do is drop the point into the equation for the plane and divide by the norm of W, and that gives you the distance of the point from the plane. Everyone with me? Okay, so beautiful, right? And now, so we've gone to this, we've gone to this, okay? And finally, one last thing. Suppose I plug in this point X prime into the equation for the plane. Will the result always be positive? When will it be positive?
Positive.
If it's in the direction of W, it's going to be plus P times W over norm W, right? If it's against the direction of W, it's going to be minus d times non-W. Right? So basically what we will find is that if you have a point on the same direction as the weight vector, then if you plug that point into the equation for the plane, you're going to get a positive value. And if it's on the other side, if in the direction opposite to the weight vector, that's going to be a negative value. So, all good so far? Does everybody get everything in sense? Okay, one final bit, if I can get to this. Suppose I have a plane which is W transpose X minus B equals C. Okay? I gave you another plane which is W transpose X minus B equals 1. So this is the plane of W. What does that plane look like? What does that plane look like? Hussein?
Translation.
It's going to be parallel to the plane, correct? On which side?
So I guess.
Against W? Right?
Against what?
Where is it going to be? Are you sure?
Actually, no.
Guys, somebody answer this question.
Pointing in the same direction. as
It's
W.
going to be in the same direction as W because the result is positive, correct? And so this one is going to be here. And what is the distance?
1 by 1.
Hmm?
1 over non-W.
The distance is simply going to be whatever turns up on the right hand side divided by non-W. If you plug the point into the equation, you get a result. On this plane, the result is always 1 divided by non-W, right? So this distance is going to be 1 over non-W. Suppose I give you W transpose X minus B equals minus. Where is that? What is that? It's going to be parallel to the original plane again, but on the other side. So this one will be like, there's my green chalk. Right. This one is going to be here. And what is this distance? What is the distance again? 1 over 1? Non-W, correct? And so this distance is almost 1 over non-W. And what is the distance between these two planes?
2 over non-W.
2 over non-W. So I don't know how the geometry question so far. We're going to be using this, okay? Yeah.
For that last one, is the sign pointing away from W?
Yes.
Like, is that
Yeah,
other,
yeah.
the
It's on the
pointing
other
this
side.
direction?
So I have a plane. If I go this way, it's +1. If I go this way, it's -1. Correct?
It's -1, but you've shifted the plane over. Have you shifted the direction
I
that
shifted
the
the plane
sign points?
Away from W, right? I've
Yes.
shifted it towards the.
Yes, but how have you indicated that you've now flipped the direction that the plane's
I
pointing?
flip the direction of the plane. All I have to remember, the way we said it is, the way we explained it, is have the equation for the plane. W transpose X minus B, right? Equals 0. If I want to find the distance of any point from the plane, I just drop it into this equation and divide it by the norm. Correct? And if my point is on the same side as W, this result will be positive. If it's on the other side, the result will be negative, which is why I make a -1. That's it.
So the direction that the plane is pointing comes from W.
Exactly.
I just don't really have a direction. It's kind of a construct.
Yes.
Yeah.
Plane is a constant. Right? I mean, that's the norm to the plane. The plane points in one of the directions, the norm, right?
What's the other direction if you just.
So one of the directions, either in this way or that. Okay, so far so good, right? Here's the first pole, and where are the poles, guys? Still a drink.
Where's the work?
Sure.
There's 90URL.com / MMSP.
I don't think there's a dash before the 23.
There's no dash.
There's no dash before 23, right?
None of this direct.
Oh, never mind, it's changed.
Then they delete that. But one. Okay. Okay, so true or false? False. Guys, can everybody say false together? Please, Alright, please. 1, 2, 3, go. False. Thank you. Right. So this is the equation of a plane orthogonal W and a distance b from the origin. No, it's a distance. B over norm W. So, okay. And now that I have established this, I can use the equation for the plane and create a classifier. We know the equation for the hyperplane, W transpose X minus V equals 0, right? Now, if I take any data instance and drop it into the equation for the plane, if it's in the same direction as W, the result is going to be positive. If it's in the other direction, the result is going to be negative. I can just look at the sign and decide if it's a positive class instance or a negative class instance. Right? Very easy. So this is a linear classifier. And the class is given by the sum. So now, let's go back and deal with the problem of learning a linear classifier. I have this bunch of data points, and I want to find a separating hyperplane. There can be any number of separating hyperplanes. All of these can be separating hyperplanes, right? So how do I decide which of these? I could use any of these, and any of these work on my training data. I want these to be maximally likely to also work on my test data. So I want to use the most conservative boundary. Now, how do I define conservative boundary? The boundary which is the largest distance from both classes. And so I want to find a classifier that's maximally distant from the closest instance. There are two different ways of doing it. I can say I can find the boundary that is the maximum distance on average from all of the training data points on both sides. That's one answer. That's not conservative. That's just taking a statistical average, right? And that's a closed form solution. But then what I really want to do is conservative, right? Being average means that, if I have data which are very dense in one class and not very dense in the other class, the boundary is going to get dragged towards a sparser class. You don't want that to happen. So you want to say, I want to find a boundary that is maximally distant from the closest points in either class. So here, for example, if I draw any odd boundary, that boundary is going to have a bunch of closest points. In this case, I'm showing you the two closest points. If I choose a different boundary, right? So these are the closest points, right? If I choose a different boundary, these are the closest points. For this guy, these are the closest points. I want to choose the decision boundary where the distance of the closest points is maximum. Now you're familiar with the idea, but the picture explains this, right? So this is all we are trying to do. So this is our maximum margin classifier. It's giving you the maximum margin to the closest training instances because that is conservative. Okay. And this maximizes the chance the classifier will work well on new unseen data. Now, what happened? So here's the problem. I have to find the boundary that is maximally distant from the closest data points. Now, when I draw an example like this, it's all very visually clear. It makes sense. You can see what are the various possible closest points. But in real life, if I just give you a bunch of data points, you have to decide which are the closest points and then find a boundary midway between the two, right? So that looks like a combinatorial optimization problem. I have n data points from one class and data points from the other class. I can have all of them could be on the equally distant from the best case boundary, right? So I have to figure out which subset of data points from the first class and which subset of data points from the second class to choose and use those to find the boundary that is equally distant from both subsets of points. That looks like a combinatorial optimization problem. It's a very complicated combinatorial optimization problem. You would have to say, okay, let me just take maybe pick these two guys I pick these two guys. Now, can I draw a boundary which is equally distant from all four? If the answer is no, okay, I throw that away. Then I say, okay, I'm going to pick these three guys and these four guys and try it. You have to do this for every possible combination if you're doing that. And obviously, we don't want to be naive. It turns out that we can do this in a closed form, kind of, not a closed form, but in optimization, using an optimization framework. And so here's what we do. For any decision boundary, we can draw these two planes on either side, which we just did as a part of our little exercise, which are a distance of 1 over b from the 1 over the boundary, right? So I can just draw these boundaries, which are W transpose X minus B equals 1, and W transpose X minus B equals minus 1 is the direction away from W, plus 1 is the one direction towards W, right? And now, if I pick any odd boundary, so I just randomly choose a boundary over here, then if I want to find the closest points on either side, what do? I just draw a couple of boundaries very close, very distant, and then begin pushing them around. And I keep pushing them till they touch a data, right? So I can keep pushing them up. And the distance between the two, as we saw, is 2 over lambda. We've already seen this, right? I can begin pushing them away slowly. And the way I can push them away, how can I push these planes away?
Minimize.
The only control I have is the norm of W, right? I can just make the weight vector longer or shorter. And if I make the weight vector shorter, the distance between these two planes increases because the control I have is equation of this equals 1 and minus 1, right? And so by just shortening my W vector, I can push these vectors away till they touch the closest data point. And then, firstly, I know that, how do I know that it's as far as possible in the two data points? That I don't have any other data point, or I don't have any plane such that, when I can push these planes further away. So here's what I'm going to have to do. I start off with some initial guess. I put a couple of planes on either side, and then I begin moving away till they touch, one of them touches a data point, right? Then how can I increase the space further? By moving the central plane out so that the other plane moves further away till that one touches the data point as well, right? And so that way, so we draw a figure. If I have something like this, I have W transpose X minus B, but this is my plane. So let's say I have my two data. Okay. If I've drawn my original plane like so, and then these are my two boundary planes, I can keep pushing them, and I shorten W. Both of them are going to move by the same distance. And so eventually, this one goes here. Is this touching the boundary? It's not, right? So how can I push these planes further away? This point. I can modify B. I'll just move this guy out, and correspondingly this one will move as well, right? So now I can move my center of the plane itself until I'm touching points on both sides. Does this mean that I have found the optimal decision boundary, the optimal boundary? No, because then this may not be the best case. So I have to figure out how I can rotate and move there, right? And so you want to in this case, somewhere in this we're going to take them. Okay. Right here. So here's what I will be doing. I'm going to be sort of moving them. I'm going to be moving my plane and the boundaries on either side and adjusting them till I find a boundary such that the boundary planes are as far away as possible and touching points on either side, right? And this would be my solution. So this is a search problem. I'm going to have to figure out how to adjust my boundary and move the planes on either side so that the planes on either side are as far as possible while keeping the points separate, right? So this is the search problem. And it turns out that it looks complicated, but the whole thing can be solved in a closed form. And the way we can solve it in closed form is to just solve the problem like so. You're going to say, I'm going to maximize the distance between these boundary points. So which means I want to minimize the norm of W. But I'm going to assume for now that my data points are perfectly separate over linear classifier, right? So I want to minimize the norm of W, which means decreasing the length of W will expand the gap between the boundary planes. But I also want to be able to rotate it so that it finds the optimal plane. And so I want to find a formalism that explores both options simultaneously, increasing the space between the boundary planes and rotating and shifting W as well, right? And so I want to minimize the square norm of W so that it maximizes the distance between the boundary planes, while ensuring that all of my training data points are on the correct side of the boundary planes, because I want to move these boundary planes till they only touch a point, right? Which literally means that all of my training data points from the positive class either lie on this plane or to the right of it, right? Similarly, all of my training data points from the negative class either lie on this plane or to the left of it, right? So how do I know if these guys lie to the right of this plane? How do I check that?
The substitute points of the equation would be greater than
So I can just substitute these points into the equation for the boundary plane, and the result must be positive, correct? Because in the same way, in the same direction as W. And what about these guys? Negative. I can just substitute them into the equation for the other boundary plane. The result must also be negative. And so you're literally saying for positive training data instances, I can say W transpose X minus B minus 1 should be greater than or equal to 0. For the negative data instances, I can say W transpose X minus B plus 1 should be less than or equal to 0. And so I want to find, so these are separately stated for the positive and negative classes. I can combine them both in one equation now. So, right, which says, which you can check. If it's a positive class, then you want W transpose X minus B to be greater than or equal to 1. If it's a negative class, you want the negative of it to be greater than or equal to 1. And so I can just write this down generically for all of my data instances. And so you end up with a optimization formula. I want to minimize the length of the weight vector, the norm of W, or equivalently the square norm of, we like square norms because they're quadratic, such that this condition is satisfied. It's very tricky, nothing complicated. You could derive this in this once you think about it, right? And once you solve for it, what we will find is that you're going to find the and this can be solved using one of many techniques. You know of various methods, right? We've done this in the optimization class. How would you do this?
Use quadratic programming.
Quadratic programming. Just based on what you know from class, how would you do this?
Gradient descent.
Certainly.
Gradient descent.
Gradient descent. You could gradient descent is one, but you can use how do you impose the constraints? I can just throw those things in as using Lagrange multipliers and then use gradient descent and optimize, right? You guys can solve this. You don't have a meter line. So this is very simple. So everybody with me so far, right? The solution is this solution will maximize the margin. So it's a max margin classifier. And it turns out that the vectors that are on the boundary are all the vectors that you need beside your classifier. The rest of them are irrelevant, right? So now going back to the original problem of what are the optimal alphas? Alphas are going to be 1 for the guys on the boundary and 0 for everything else. And so here's a roundabout way of solving what we just said. Everybody with me so far? Questions? So this is a support vector machine because you're only using those vectors on the boundary plane, which are called support vectors. Yes.
But what happens if your test point is in between them?
So it's going to be, well, so long as the test point is to the right of the plane, it's going to be on the correct side of the plane. It's going to be correctly classified. This is the most conservative bound, which maximizes the room for the test, the space in which the test data can fall and still be correctly classified.
But in this particular example, the red boundary will classify everything as red to the right, and the green will classify everything
No,
as
so
green to the
everything
left.
to the right of this guy is going to be classified as.
Oh, okay, got it.
You're just maximizing the space between, you're finding the most conservative boundary, that's it. And any other questions, yes, sir?
How do we find that first boundary itself from which we start expanding?
So you can initialize it. This is just an optimization problem, right? Find me a W such that this is the problem. Find me a W such that the square norm of W is minimized and the condition is sense. This is just a straight up optimization problem.
What if that done?
Okay, that's good. Okay, that's first.
So this is true.
What do you see? Want to go watch your face or something? Okay, I'm the guys, true or false? False, okay, that's what's interesting, right? So everything that we've done assumes that the classes are linearly separable, right? What if the classes are not linearly separable? They cannot be separated. What if the classes can be separated but not by habit? And what if they cannot be separated? No, even by a non-linear plane that you have chosen, function that you have chosen. We're going to have to deal with all of these cases, right? So let's look at the first one. What if they are not same? I've got red dots plonk in the middle of my read space and green dots plonk in the middle of my red space. So now I finish. And now here was the original problem. This original problem said that you have to minimize the square norm of W such that those conditions are satisfied. All the positive data points are to the right of the positive plane, boundary plane. All the negative data points are to the left of the, on the negative side of the negative boundary plane. And this, so long as you ensure this condition was met and optimize W, you got the correct solution. It says that in this case, that condition is never going to be met. There is no boundary plane which guarantees that all the red dots are to the right and all the green dots are to the left of the other boundary plane. There's no such claim, right? So how do we deal with this situation? So here's where we introduce this critical data called the slack variable, right? Now here, let's just say, go back and consider our classifier. Here's the classifier already. We have two boundaries, right? Now, for every data instance, I'm going to introduce something called a slack variable. This slack variable is telling me how distant it is from the appropriate boundary plane, how distant it is on the wrong side of the appropriate boundary plane. So the slack variable for a positive data instance, which happens to be on the negative side of the positive boundary plane, is going to be this sum, right? Similarly, the slack variable for a negative data instance, which is on the positive side of the negative boundary plane. So every data point is going to have its own side card, whatever, however you read for now. I call it side. Okay. This distance tells us how wrong that data instance is vis-a-vis the boundary plane itself, right? And so now, if I want to find my boundary plane and I still want to be conservative, then what do we want? We want these boundary planes to be such that the distance by which the non-separable data instance is on the wrong side of the plane should be. So you want these sides to be small. You want the boundary planes to be such that when you have something on the wrong side of it, it's not too far. Makes sense, right? And so we're going to explicitly minimize these distances. So the way we will do it is try to find the boundary place inside this here. If the total length of the slack variable varies with the boundary. If my boundary plane is out over here, all of my red points are on the wrong side. Similarly, all of the green points are on the wrong side of the sky, right? So the total size is going to be the sum of distances for all of these guys. Where must the boundary plane be to minimize this guy?
Closer to the.
Where must where to minimize the slack? Where must it be? It's going to be right there, right? If it's lying right on the boundary, then this is the best case. Because the boundary planes are in the correct direction, right? The positive boundary plane is on the positive side of the decision boundary, so you can't push it to the other side. So this is the best case for the red dot, and so also the best case for the green dots, right? This is where we have. So this is the best case for the slack, for the slack. And then what is the problem with having the boundary planes of plus? They're too close, right? And so you have these two criteria. If the boundary planes are very far apart, you're going to find a great number of data points on the wrong side. If you make the data points, minimize the distance of the data points on the wrong side, then the boundary planes end up being too close. And so we have to, if the boundary planes are too close, the planes violate our desire to maximize the distance between these boundary planes. And so we have two contradicting requirements. You want to push the margin planes close together to minimize the totals. But at the same time, you want to maximize the distance between them to make the classifier as conservative as possible, right? So the second one is kind of giving up on the misclassified instances. The first one is trying very hard to account for the improperly placed instances and then have some kind of a push between the two. So here's what we want to do. We want to simultaneously maximize the distance between the planes while minimizing the slack, right? And we can formalize this. That's not very hard. For this, we need a formula for the total slack first. And here's how we can do it. What was the equation for this? Anybody remember?
X minus B.
So yeah, the equation for this plane was simply W transpose. So if this was my boundary, this was W transpose X minus B equals 0. The equation for this plane was W transpose X minus B equals 1. Correct? Everybody remember? So if I have a data point on this side, which is misclassified, how far is this data point from this boundary? How far is it?
Slack bit. Slack bit on bit.
The slack way, but in terms of the equation, how far is it? I just drop it into the equation, right? So let me call this X. That distance is going to be W transpose X minus B minus 1, right? Unnormalized, not normalizing by W, because the length of W is what I'm trying to estimate, right? So something that's on the wrong side of the positive X boundary is going to be this distance from the boundary. Something on the right side is also going to be same distance, right? If it's on the wrong side, what's the sign of this? Negative or positive? Negative, right? So we're only interested in the positive margin plane is given by W transpose X minus B equals 1, right? It's a distance of 1 over 1 boundary, precision. And any data point that's to the wrong side of it, any data point at all is going to have a distance W transpose X minus B minus 2, right? But we're only interested in the guys that are, on the wrong side. So for the guys on the wrong side, this value is going to be negative. I can flip the sign, I can negate it and make it positive, right? I can say 1 minus W transpose X minus 2. Everybody with me? Right? And so now this term is going to be negative for correctly classified instances or things that are on the appropriate side of the boundary. It's going to be positive for things that are on the wrong side. And since I'm only interested on things that are on the wrong side, if anything is negative, I can ignore it. If anything is positive, I must keep it slack. That makes sense? So all okay? So that's it, right? So I have a formula for each data point. I have a formula for how far away it is from the boundary if it is on the wrong side. If it is on the correct side, that value is going to set to 0. I need a similar formula for this other plane, right? The equation for this plane is W transpose X minus B equals -1, right? Or I can just say +1 equals 0. So if there are any data points on this side, just plug them into the equation. And so all data points on the positive side of the negative boundary plane, I can compute their distance from the boundary plane by sticking them into this equation. And that value will be positive for all the data points on the wrong side. And it's going to be negative for all the data points on the correct side. So once again, the unnormalized distance for any data point over here, simply 1 plus W transpose X minus B, right? And I can, since I'm only interested on data points on this side of the plane, for the data points on the other side, this value is going to be negative, right? I'm not interested in the negative values. So I can just choose the max of 0 and the result of just dropping the data point into the equation for the plane itself. And now I get the distance from the plane for all the data points that are on the wrong side of the negative boundary plane, right? So did I confuse you guys or does it make sense? You guys at the back, right? They're all very quiet. Did it make sense? Anga, make sense? Yeah, question?
No, this makes sense. But when you said initially when you were talking about the nearest neighbors, like why is that wrong? That
We'll get to that, right? Yes.
How do we decide which points are wrongly classified in the first?
For any plane, right? This is if I give you any plane W transpose X minus, then the corresponding boundary plane is W transpose X minus B equals 1, or W transpose X minus B equals -2, right? So for any choice of W and B, these are the values. And so our job, so basically, for the negative instances, this was the distance, total distance of all the points on the wrong side of the negative boundary, right? Which is max of 0 and 1 plus W transpose X minus B. For the positive instances, this was the total distance of all the data points on the wrong side of the decision boundary, max of 0 and 1 minus W transpose X plus B. So I can combine the two into a single formula and say that for any data instance xy, the distance from the if it is on the wrong side of the margin plane, then the distance is 1 minus y times W transpose X minus B, right? So in general, the distance of any point from the margin plane is max of 0 and 1 minus y times 1 minus W transpose X minus B, right? So this only accounts for data instances which are on the wrong side of the boundary. And this is what we want to minimize, right? Yes, yeah.
So fixing the margin as 1 by lambda.
1 by over number.
But so it can't be like 2 over.
You can choose 2 if you want. It's just a easy process, right? It won't make any difference. Won't make any difference to your solution. It's a scaling back, right? Yeah. It automatically comes out of the 0, max of 0 and 1, right? So we want to minimize the square norm of W such that, so minimizing the square norm of W is trying to maximize the distance between the planes such that this term is also simultaneously minimized. This is called the hinge loss. It's a hinge because for negative values it's 0, positive values it gets its value, right? And so the two objectives must be traded off. So you can just combine them into one single solution, right? Where lambda times the square norm of W, square norm of W is what it has, plus the average hinge loss of all of the data instances. So this makes sense to everybody? We arrived at that one step at a time, but you can actually do this in your sleep. It's nothing complicated. So long as you know what the equation for a hyperplane is and what the equation for the distance from a hyperplane is, the rest of it just falls into place one step at a time. There's nothing magical going on. Questions? Okay. And so this can be this is an optimization problem. Now there's a question here. What is the value lambda? So lambda is the value that trades off between how important it is for the boundary fields to be as far as possible and how important it is for us to never misclassify any training data instance. And typically what you would do is to have some handout validation data on which you're going to test for different values of lambda and pick the value of the lambda that gives you the best performance and validation data and use that and go back and solve the issue problem. So this is basically lambda's computer using handout training. This is kind of again. So there's an equivalent formulation. I mentioned the slack variable earlier. There's an equivalent formulation which is exactly the same as before. Nothing has changed. Instead of saying that I'm going to be minimizing square norm of W plus lambda times the distance, I can just say instead that I'm going to be minimizing the square norm of W plus C times the slack variable, subject to every point is no greater than the slack variable distance from the boundary. That's correct. These two are exactly the same solution, yes.
Rather just C, where is it about that?
C is actually the same as lambda. Actually, no, there I applied lambda to W, so it would be the way I wrote it earlier, I had lambda applied to W, right? So I could everything together. So, yeah. Okay, time's up. The first statement true. We must use the information from all vectors in the training samples to calculate support vectors. So classifier can be represented by a sign. The sign for any separating argument true or false. Right? The support vector machine can find the classifier that has the maximum distance from the closest instance to either class so that it can minimize the chance that the classifier will work on nuanced data, true or false. Right? And we can turn the problem of finding the hyperplane to a quadratic programming problem. So we can use all kinds of convex optimization. Right? Second case, we can use the SVM with slack variables for the case where the data are linearly separable except for some outlier instances, true or false. Right? And we need to maximize the margin as well as the slack variables. Okay. And we can use convex optimization methods such as Lagrangian dual scattering. So we just saw we could, right? And we can only use a K4 class validation. So yes.
First statement, because the starting we don't want.
So the point is, in the hypothetical case, right? If you throw away a whole bunch of things and they're towards the boundary, you're still going to get the correct answer. You don't need all of them to find the support vectors. It is true that you don't necessarily know which ones you can throw away, but in principle, there's a subset here. Basically, it's a tricky option.
Is it more like points that are correctly classified don't contribute to the support vectors, or but they're still used to calculate because like in the hinge loss it becomes 0.
So yeah, they don't actually. So the point is, if you threw them away, they're not going to have. They're not going to create a
Yeah, but then it's they still don't know which subset of lambda are used.
Again, in principle, if those were missing, it wouldn't make a difference. Right, that's it. So we've dealt with linear boundaries. How about things with non-linear boundaries? So this becomes easier. And for us to deal with this, we're going to go back and we call the Lagrange method, right? So the Lagrange method basically said that if I have some constraint gxy equals c, then I can just put lambda equals plus lambda times g of xy minus c. And this was a barrier function, right? If I was minimizing this with respect to x and y, what must I do with respect to lambda? Maximize it so that if the condition is violated, it just blows up, right? And if I'm maximizing with respect to x and y, what do I do with respect to lambda? Minimize it. Again, the condition will blow up, right? So this variant, which we also saw in the optimization class, is what is called the Kalsh-Tucker solution, right? And here, again, you remember this from the optimization class? How did we solve it?
Linear equations.
We again had Lagrange multipliers, right? But what was the condition on the Lagrange multiplier?
Greater than
So for the equality constraint, you had Lagrange multipliers and they were unconstrained, right? So anytime the constraint was not satisfied, you could always choose a Lagrange multiplier so that your objective function went very swung wildly in the wrong direction. Right? When you had an inequality constraint saying g of x got to be less than 0, then if I was trying to minimize this function, there was a constraint on lambda. What was that? It always have to be positive, right? Because if you let lambda be negative and g of x is negative, you can still sort of spin lambda and make it a very poor solution. But if lambda is always positive, then anytime g of xy is negative, so g of x is negative, there's nothing I can do to lambda to change the location of the optimum. But if g of x becomes positive, then I can just make lambda really large, make that portion of the objective really large, and give you a really crappy solution. So this has a way of constraining my solution to make sure that my constraints are satisfied. The g of x is negative, right? So the optimization problem again was that you had to maximize this with respect to lambda, and you had to minimize this with respect to x. So there's a very there are two things going on over here. One is a minimization on the outside, and the other is a maximization on the inside. Can I change the order of the max and the min? No. Why not? What is the condition under which I can change it?
List convex equal x.
So anybody? So it turns out this is a again. Let's go back. Let's see where that was, right? So this is let's go back to our linearly separable case. I'm not speaking of nonlinear problems at this point. So we wanted to minimize w squared subject to these constraints, right? I could have written that in terms of Lagrange multipliers as we saw earlier, where I'd be maximizing this with respect to alpha. And I have our min outside and a max on the inside, right? Now it turns out there's a very special class of functions of this kind where I can change the order. So these are the ones that satisfy the KKT conditions, they're saddle functions. And so you can see why. So here, if I'm trying to find, look at this. If I'm trying to find the W such that the maximum value over alpha is minimized, right? So if this is my W, consider this W. If W is here, the maximum value over alpha is right here, right? if W is here, so maximum alpha is over W, over alpha is right here. So at each value of W, I can plot the maximum with respect to alpha. Correct? And that's going to be the slope out here. This curve here. This curve is going to be the maximum with respect to alpha and each W. Make sense? Right? And then that curve is what I want to find the minimum of. And that would be right. Here, where what happened? That would be right here. Okay, so you can see how for each W finding the value of alpha by which we're finding the maximum with respect to alpha gives me one function, and then I'm finding the minimum of that function. Right? But then here's what I can do. For each alpha, I can find the minimum with respect to W. And so here, the minimum with respect to W is going to be here. For this value of alpha, the minimum of W is going to be out here. For this value of alpha, the minimum of W is going to be out here. So for each alpha, I can find the minimum with respect to W and find the alpha for which this value is maximum. And that too is going to give me the same solution. That makes sense? So for this particular class of functions, things that look like saddles, we satisfy the Karish-Kuhn-Tucker conditions. And there, it doesn't matter whether you do the max first and the min later, or whether you do the min first and the max later. And so in that case alone, I can, instead of saying R min max for alpha, I can just take the R max over alpha and the min of W inside. And I still get the correct answer. Okay, I just flip the order of the max and the min. And now this is what is really cool, because once I push the min inside, then the term on the inside is a quadrant. I can solve for it. I can differentiate with respect to W and B. If I differentiate with respect to W, I get the weighted sum of W is simply the weighted sum of all the x's. So this looks a lot like the weights that we got for the nearest neighbors, right? Doesn't it look like that? You're going to get some other solution for the B's. I won't actually go through the solution. That's fairly straightforward. But eventually, when all is said and done, you're going to end up with this solution, which says that you want to find the alphas such that the sum of the alphas minus this ugly looking term on the inside is a half there is maximized. Does that look familiar?
Yeah.
What does it look like? Exactly, right? So we started off with the solution. And I spent 10 minutes telling you why the reverse is right. And it turns out that when you actually work through the arithmetic and use the KKT conditions, and again, the arithmetic is very trivial. There's nothing particularly complicated about this arithmetic. All we did over here was I minimized the inner side with respect to W, which means that I can differentiate with respect to W. I have a half just for convenience. So W equals, if I take the derivative with respect to W, this goes away summation alpha I Wi xi, right? And then if I differentiate with respect to B, that's going to give me, again, look at this guy, but the first term has no B in it. The second one is simply going to give me the summation of alpha I yi is 0, which tells you something very interesting, that they're going to be choosing as many positive as negatives, right? If the alphas are all binary. For your support vectors, you won't have more positive instances than fewer negative instances. The average has to be 0. And then you just plug those in and you end up with this very cool formula, which you could have derived without actually going through all of this, starting with the logic that we began in the first few minutes of class, except that you'd have been 100% profit. Right? So it just turns out that very often our intuition can't fail us, right? The math will tell you something that's exactly the opposite of what you need to do. What do you think? And so we're going to solve for alpha I also, right? We want to maximize find the alphas that are all positive, such that the sum of the alphas minus the total accuracy on the training data. Crazy enough. So you're subtracting the total accuracy of the training data. This is maximized. And the outcome is that alpha will be non-zero only for the support vectors, the ones that are on the boundary, and they're going to be 0 on the boundary, and 0 for the rest of the instances. And you observe something else interesting over here. And what you find that's interesting is that the weights look like this, right? And moreover, if you look at your optimization function, my optimization function has only inner product terms, right? You see what happens over here. So my optimization function is the sum of alphas minus the sum over all ij pairs of alpha I, alpha j, yj, etc. Mass for 16. That's all inner product terms. What kind of classifier were we computing? This was a linear classifier, right? Now, suppose I wanted to build a non-linear classifier. What would this tell you? I can just replace those inner product terms with a. So again, know the optimization is in terms of inner products. The weight, like so. So your classifier also ended up just being in terms of inner products. It's exactly your nearest neighbor classifier, right? Nothing more. With the extra B term for a bias. And so I can replace all of these inner products with currents. And I'm going to be ending up running a classifier in a linear classifier in a high dimensional space, which would be a non-linear classifier in your field space. And so that's a standard kernel-based support vector machine. Very straightforward. Again, you don't actually have to work through all of the arithmetic of SVMs, right? You could start off with your nearest neighbor classifier. With implicit and implicit, with the memory, then whatever you end up with is 100% wrong. And then flip the sign, they're going to end up with the correct solution. Right. And so this again is a standard quadratic programming problem you can solve it. We're kind of okay, first statement, third false. Second is also right, both of them are true. The KKTs, the Karushkum-Tucker, what was the difference between the KKT and Lagrangians? The standard Lagrangian that we heard, studied. What was the difference, guys? So for the Lagrangians, we only consider equality constraints. Once you began considering the inequality constraints, this fell under the solution, right? And we actually showed the specific solution that we saw only works if the function satisfies, looks like a saddle function, because we have the saddle point. That's your that's Karush-Tucker's theorem. But we don't need the math as far as what we can know. Our problem is concerned in how to use it. So, and what are the SVM kernels? Of course, standard linear kernels, which is still linear. You can have polynomials. So you can have Gaussian radial mixes. We've seen these before. The Gaussian kernels actually end up living in an infinite dimensional space. I have sigmoids and all of things. Again, any function that satisfies Mercer's conditions. It's a valid kernel. Anybody remember what Mercer's condition was? Symmetric. Symmetric. What was Mercer's condition? We just said that it basically said, if I remember this correctly, for any choice of A and B, summation ij, bi, ej, summation xi, xj must be. That's all. That was the only condition we had, right? And this was based on this basically computes the squared norm of any composed vector, the high dimensional space, right? So, they're Lagrangian domains, let's get this stuff, right? Anyway, so standard approach for support vector machines, choose a kernel function, choose a efficacy side of the and construct your discriminant function, which is your classifier, the one with your solution. So we'll stop right here. I ended 1 minute early, so you get some pictures. And if somebody wants to read a sword, I sword I have them last minute for me folks. Thank you for coming. Someone who's not wearing a mask maybe wants to take a video. Okay,
I don't know. Friday and Saturday.
you got long hair, you can get on it.
Sure, yeah.
Those monsters.
I thought that was today. I was like,
Come on, guys.
I got one problem. Crazy to say the problem. I vote for it.
Come on, guys. That's your favorite thing. We need to have some products. I think the most monster you can think of. Does that look scary?
Yes.
Come on, guys.
So fine.
Thanks so much.
There's like nothing you can do with this. Yeah. It's a unicorn, right? All people at the back, please. All right. Where's this? Take a few. Hold this one up. Good. Take another. Come on. Okay, come back up, guys. Back up. Where's my witch? And then, oh, witch, come on up. You're the one holding me. Wow. The sword. Hold that up. No, hang on. I gotta take my cheese. I gotta take this one. Okay. I refuse to be photographed with a microphone. Tease.
So it is.
Smile your most simple smile. Show your teeth.
That's 4.
Thank you.
Perfect.
I've done these things, guys, because I need it for next year.